Hello everyone, let me introduce myself. My name is Prisilya Yacobus with student ID 2410110600012. I'm from Information Systems A class of 2024. Now I'm going to explain the concept of the crossing number or graph crossing number. Enjoy watching. Friends, have you ever noticed how complicated the wiring inside our smartphones is? Or how airplane flight routes are arranged so they don't collide in midair? In mathematics, this problem of path management is studied in graph theory, specifically the concept of the crossing number. In this video, we'll learn more about the crossing number entitled Understanding Crossing Numbers, the Art of Avoiding Line Collisions in Graph Theory. Simply put, the crossing number is the minimum number of line crossings or collisions that occur when a graph is drawn on a plane. Remember, these crossings can only occur between lines and cannot collide with other vertices. As a starting example, let's look at this simple box graph. If we draw diagonal lines through it, it will form an X-shaped shape that intersects each other midway. This intersection point is called a crossing point. In the real world, line collisions like this are strictly avoided because they can cause problems such as short circuits in electronic components. So, what's the solution? This is where the art of mathematics comes into play. We can use the trick of curving lines. Notice the changes in the following graph. If we draw one of the diagonal lines and curve it around the outside of the square, there will no longer be any lines that collide midway. If a graph can be successfully redrawn in such a way that it is free of crossings, it is called a planar graph. Because there are no collisions at all, a planar graph has a crossing number equal to 0. However, can all graphs be solved neatly? Unfortunately not. Let's test it with a very famous classic puzzle, the 3 houses and 3 utilities problem. Imagine there are 3 houses at the top that each must be connected to the water, electricity, and gas lines at the bottom. There are a total of 9 connecting lines that we must draw. No matter how hard we try to rotate, curve, or move its paths in a plane, this graph will always leave at least one absolute intersection that cannot be eliminated. This deadlock proves that the utility graph has a crossing number of 1. The concept of minimizing crossings is crucial in real-world applications, especially in the design of microchips and printed circuit boards, PCBs. By knowing the crossing number, engineers can determine when they can create a cost-effective single-layer circuit, or when they should start using multi-layer circuit technology to separate the electrical paths to keep our devices safe. In conclusion, the crossing number helps us transform mathematical complexity into technological efficiency. I, Prisilya Yacobus, thank you and goodbye.